having said all that, let's go ahead and get started. This is our final topic, our final content of the semester, the high-level topic of algorithms. Let me just mention, though, that, and I have hinted at this before, that this is an important topic, I think, beyond just knowing how to program, being able to understand software. Those are really two different things. And it is sufficiently important that it's really a class or a number of classes that those who choose to really specialize in computer science side of things get the opportunity to take. As electrical engineers, you have the opportunity to kind of go a little bit more in depth down the software development side of things, but it's hard to do that while also having some electrical engineering specialization. So we will cover this in a day or two, but in reality, it is a few semesters to really gain deep expertise. So I'm not trying to pretend we can cover it all in any real way, shape, or form. In terms of a valid kind of learning outcome from this week, it's really more about fluency in the concept of algorithms, an appreciation that there is this idea of analyzing implementation via algorithmic analysis, and just a little bit of exposure to what differences there could be between different algorithmic approaches. And that's probably sufficient. It's all bonus content, as I've mentioned, even starting last week. As our sort of final reminder, a week from today, demo day, technically starts at 12, so we're getting comfortable starting at 12:05, but it starts at 12. We have the full 2 hours, and I kind of scoped it out that I think we'll use pretty much the entire 2 hours, so we really have to kind of stay on track. I had sent a Canvas announcement and posted on Discord as well, a set of Google Slides, kind of just edit for your presentation with a pretty high-level template for what I think would be a reasonable presentation for each team to put together. I wouldn't stress out about that, meaning, doing an amazing job of that doesn't really doesn't make a difference in terms of your rubric and grading. It doesn't change the fact that you did or did not get some particular feature of your project as proposed done. But it's always good to give a good presentation if possible, right? So in terms of putting together the slides, I don't expect that to take more than 30 to 40 minutes, an hour as a team. Just sit together, type out a few slides, but then kind of plan it out just briefly. Like, get together briefly before, maybe just Monday morning could be sufficient for that, and say, okay, I'll talk, I'll introduce, then we'll switch, you'll talk about this, then you'll talk about this, and just have something that flows. It's just awkward for everybody when a team gets up here, and I will ask you all to come up here on Monday, and nobody knows what to say next, and you're just kind of like, I don't know. So just take that hour plus and just be prepared for Monday, recognizing that that's something that you do, and hopefully do very quickly after you've actually finished the rest of your project. So let me know now or later about any questions you have about that. But I think if you look at the Google slide deck, it's just the starter template. Have fun with it within reason with regards to that. Try to keep it within that time range. I'd hate to have to cut teams short. I know that for many of you, as you feel very passionate about maybe some of the code that you've worked on, you really kind of want to show every line of code to the rest of the class. We just won't have time for that. I will look at every line of code, but to the rest of the class, we won't get to see it. So try to keep it within that reasonable time frame so everyone gets an equal chance to present their presentation. Okay, so what is an algorithm? It is a term we've been using on and off all semester, sometimes correctly, sometimes a little bit loosely. Just a fancy word for a sequence of steps to describe how to solve a particular problem or how to perform our particular computation. So given that definition, algorithm, a series of steps to implement something via computing, we have been doing algorithms all semester based on that definition, and that is correct. Anytime you write code to solve a problem, you are implementing an algorithm. Usually, when we refer to something as being an algorithm versus the code to implement it, we are focusing more on kind of the theory side of things, more about being able to more formally reason about the solution, whether we can somehow prove that the solution is correct. We don't do a lot of that this semester. We kind of run it and say, yeah, it looks good enough. But with algorithmic frameworks, you can start to reason about the correctness properties of a given resulting implementation. And I think more immediately and more commonly, we use algorithmic notation to help us reason about how long a particular implementation would take to execute. So we've been doing them all semester in the sense that we've been implementing algorithms all semester. Today we're going to take a small step back. We're going to code a lot less today and on Wednesday, and a little bit more looking at code or looking at so-called pseudocode to understand a little bit of those high-level properties of algorithms that can be very useful before, while, or even after we go through all the effort of doing that implementation. This is very much a fundamental topic in computer science. Oftentimes, I would say that's what kind of differentiates a computer science or a person with a background in computer science versus just a programmer. Programmers should have some potentially deep understanding of implementation aspects. Someone who has a computer science background, typically they also can do implementation aspects, but they have a more formal training in terms of reasoning, mathematical foundations of the underlying implementation. There is a course you can take here. The kind of core algorithms class is taken by mostly computer engineers, computer science students, and software engineers. It's considered one of the harder classes. You may not get a feel for that this week, but that's okay. The prereq chain is kind of tough for for non-computer science or computer engineering students, so it's probably unlikely you'll get there. You can always, hey, you're a student, you can always learn outside of the course. There's a very famous book, CLRS book, you'll also hear it referred to. It's a very famous reference. If you're just bored over the summer, grab that from your local library and explore all the wonderful algorithms. It's a very thick book. The book that a lot of people have on their bookshelf but haven't actually read is the so-called Art of Computer Programming. It's not quite done yet. It's Donald Knuth's kind of life work, and he's been working on it for over 50 years. And it's in his attempt to cover basically the encyclopedia of knowledge as it relates to algorithms. And a lot of people claim they've read it. They've probably just read excerpts because it's actually quite difficult to get through. But this, as a textbook, is a very good book. So after this class is over, semester's over, you want to learn more, of course, take some programming classes, pick up a new language or a new framework, and just explore on your own. That's something you should now feel a little bit more comfortable to do. Certainly from within that Replit environment, it makes it pretty easy to get started with a new language and or framework. If you want to learn more about a little bit of the foundational theory behind what we're all doing, that CLR book is a pretty good one to pick up from the library. So what does an algorithm look like? We haven't been using this slightly more formal way of doing it, but the other term we have used is really just so-called pseudocode. Not actually necessarily something that you can take and directly compile, but a slightly more formal way of just reasoning about what is effectively the same number of potential steps. Usually, when we have an algorithm, we can write code for it. Likewise, when we have code, we can usually describe an algorithm that's being implemented in that code. We oftentimes want to just kind of take that direct shortcut and say, let's go implement things. That's kind of happened to us this semester, right? We started off a little bit earlier in the semester, and I was really trying to kind of write out the series of steps, and we had like TextPad that we were just kind of opening up and adding our notes. And then I said, that's taking too long. Let's just open up the code editor and just start writing code as we go. This is also kind of a more formal sort of intermediate stage as well, describing both the inputs, required outputs of what our eventual program is supposed to do, as well as then in a somewhat code-like fashion, but using a more mathematical notation, description of the steps to get from that input to that output. This is meant to be, and this is straight from Zybooks, this is meant to be a very straightforward algorithm example here, right? The so-called linear search. To search for something means to find where some value is located in, at least this case, an array of data. So if our input is A, an array of integers, A sub 1 through A sub n, and a key or a value to search for in that array called K, we will ensure or we expect to get a value of M back out. M is either the last index of K in that subset of A, or we return -1 for when K is not found in A. Now again, this looks kind of unnecessary maybe, right? We could have written that in plain English, and in fact we had to do kind of a translation back to plain English to be able to go from this to something we could start to implement. If I'd asked you to do that, and I said, implement a linear search for an array, I expect at this point you'd all be able to do it. Write a function that takes an array as input and a value to look for, and returns either -1 or returns the index in that array where the last time that value is found inside that array. So by having this algorithmic kind of pseudocode notation, we're not necessarily gaining any programming ability, but we'll see the point here in a little bit. Otherwise, then when we look at it, well, okay, we're initializing some value m to -1, we're initializing some value n to the length of a. We know how to do that in our code then, right? We can initialize an integer value m we call -1. We can set some length of the array a either as an input or we can initialize it correspondingly. For I is 1 to n, do a for loop. We know how to do that as well in our code. If a sub I is equal to k, then our value m can be set to a sub I. That is kind of interesting that that's wrong. If a sub I is equal to k, I've looked at this slide 50 times. If a sub I is equal to k, meaning we found the value k in our array at a sub I, we shouldn't return a sub I. What should we return? No, k is our input. Okay, we have an array, a value k we want to look for. We want to return the index in which we found it. M, if we didn't find it, is -1. We go through our loop. If we have a match, we want to set m to be our index. What should it be? Just I, yeah. So it's just unintentional typo that has been there for many years. We can learn a lot about an algorithm as we've been doing all semester by implementing it for different values of n, right? For different lengths of the array. And we can learn a lot by just measuring the resulting runtime. We've done that a few times, at least to get a high level feel for, boy, that bubble sort sure is slow when we have really large arrays that we're trying to pass as input, as have been a few other of our implementations. Our kind of naive recursive factorial implementation was also exceptionally slow, as we saw. And that general approach is still something we may want to consider and is still very valuable, right? Initialize n to some appropriate value, say 1 million, generate an input of that size, run, and then time that implementation, and then change our value of n. Presumably, increase the value, change it by some reasonable range, and basically run an experiment, right? Which is, as I change n, that's my x-axis, how does my y-axis, which is the runtime, change? Plot those results of time on the y-axis versus n to discover any trends along the way. If we were to do so, what would we find about our linear search? As we increase the value of n, how would our runtime grow as n increases? It would be linear, right? Absolutely. And the whole field, the whole art of algorithms is be able to reason about implementations or reason about the pseudocode of an implementation and be able to come up with answers like that. We are simplifying that test quite a bit here, but you could do worse than just kind of counting your for loops and figuring out, okay, how many rough lines of code would I have inside my for loops here? And well, we have a for loop for size I equals 1 to n. As I increase n, my for loop just keeps getting longer and longer. And it's going to grow proportionally or linearly with the size of our for loop. That is skipping a lot of our implementation details. So there's still quite a bit of value in doing this step here, which is, how complex is my code? Well, why guess? Let's run it. Sometimes, though, there's quite a bit of value of being able to do that early analysis to determine, well, maybe I shouldn't do this approach. Maybe this approach isn't sufficient for my needs from a performance perspective. Let me potentially consider alternative approaches. As compared to linear search, we have the so-called binary search. With linear search, there's this assumption, although it wasn't explicitly stated, that the data itself is randomized. If we assume that the data is already sorted in some ascending order, then there's other algorithms that are possible, including the so-called binary search. The idea here, and binary here just means two choices or sort of two branches. It's related to the 0 and 1 of like a binary encoding of data or storage in memory, but it's kind of indirectly related. The idea being here is that you have a search for this value that starts in the middle of a sorted array, and it's kind of like the the hot and cold game, or like I'm thinking of a number from 1 through 100 type of game where possibly the ideal approach is to first guess 50, and then you'll get a result of, well, you're too high or too low. Okay, let's try that. I'm thinking of a number from 1 through 100. DD, I'll pick on you. Guess a number. Too high. Guess again. No, so first off, you're not following the ideal approach. Starting over. Think of a number from 1 through 100. Go. Too high. Guess again. 25. Too high. Guess again. 15. Too high. Guess again. 7. Yeah, you got it. Okay, so you got it on 4 approach. That is the implementation of the binary search approach, which you are going to get there eventually too. The linear search would be closer to, I'm thinking of a number from 1 through 100. Is it 1? No. Is it 2? No. Is it 3? No. Well, that's linear, right? From 1 through 100, it's okay. From 1 through a billion, that's pretty frustrating. The binary search is, assuming the data itself is sorted, start smack dab in the middle and determine whether we should keep going on, if we kind of partition the data in halves, should we keep going on the left side or the right side? Are we too high or are we too low? If we're just right, then we're done. If the number was 50, you would have gotten it correct in one guess here. But ultimately, we can either do a recursive or an iterative implementation of that, which is, while we have the value we're looking for, have our beginning part, have our end part, our min and our max value, our value of 1 and 100, calculate what effectively the midpoint of that is. Let's say that that is 50, and determine, is the value we're looking for, is it less than 50, or is it greater than 50, or is it equal to 50? This is exactly the opposite of what I just said, but effectively, if the value is larger than 50, do this again, looking at 51 through 100. If the value is less than 50, do this again and look for 1 to 49. If the value actually is 50, well then we're done. And that code at least doesn't have a typo in it. Little bit harder to reason about the performance of this, but part of the value of algorithms is to be able to do that reasoning. And again, like I said, there's whole books, there's whole tomes, there's multiple classes you take, but that's part of the value of having this pseudocode, this algorithm approach, that you can apply that reasoning to what the performance would be without having to go through and test for every possibility and run that N experiment for every type of algorithm you would potentially want to consider. That's referred to as the algorithmic complexity. We've used those terms a couple times this semester, now we're going to do so slightly more formally. Can we reason about it? It was in the Xi book, so if you've done the final reading of the semester, you know the answer. The idea being, again, I'm thinking of a number from 1 through 100. First time through, I have kind of a 1 in 100 chance. Second time through, I have like a 1 in 50 chance, then a 1 in 25 chance, then a 1 in 12 and a half chance. How does that runtime change? First, I have to look at everything, then I cut the value in half, then I cut the value in half, then I cut the value in half, etc. Do we know what operator would kind of describe that successive partitioning in half? Close. And there are algorithms that have square root complexity. They're not that as common because it's kind of hard to think about non-numeric things that operate in this way. I want to cut it in half and cut it in half. If I doubled it, if I went from 1 to 2 to 4 to 8 to 16, that would be 2 to the n, right? That would be exponential. So what's the opposite of that exponential operator? Logarithm, right? So generally we would look at this approach and we would say, once we have this input in this fashion, we can get to the index in logarithmic time. And again, that doesn't actually tell us the answer. Is linear search faster or better or worse than binary search? Ultimately, that high-level reasoning gives us a starting point to answer that question. But how it's actually implemented, even things like we've looked at, like the impact of the compiler and what the compiler can do to your implementation to minimize the amount of instructions that get emitted, can make a difference. But this does allow us to provide some high-level reasoning first off. Having said that, it's not necessarily an answered question just based on what we've just described. Linear search, we said, was linear. As n increases, it's kind of like you can think of it as like a straight line slope, right? As n increases, our runtime increases. Binary search is logarithmic. As n, this is going to look backwards on the video, as n increases, our performance kind of levels off because it's sort of logarithmic, right? Well, so binary search is consequently better than linear search? Maybe, maybe not. They were slightly different, right? Linear search assumes the data is randomized. Binary search assumes the data is sorted, so we would have to consider the algorithmic complexity of doing that sort as well. And so whether binary is more efficient than linear search maybe depends ultimately on what we're doing. And that's the kind of reasoning you can start to do once you start thinking in this mindset of what are the inputs and the sizes of my inputs to my problem. In this case, if I'm searching for one value in an array, linear search is going to be higher performant, even though it's linear in time because of the time it would take to sort the array for our binary search. But on the flip side, if I wanted to search for m values in the array, where m is just yet another parameter for our analysis, perhaps now the binary search is the more efficient way to do things. That sorting overhead would presumably just sort of be a one-time cost, one-time overhead of sorting that array in the first place, and then each search would be significantly faster with our binary search. So that's the value of having this kind of algorithmic way of thinking about things. Yes, you could always go through and say, well, I don't know the answer, let me implement it all. But it's very useful to be able to have that answer, or at least a reasonable guess as to what the right answer is, so you don't have to go and implement 15 different ways to solve a problem and just measure which one turned out to be the best. You can reason about which one may be the best for your purposes. And that's this term we've used a couple times, this big O notation. There are things other than big O, but this is the most common one you will see. It's a mathematical way of describing how an algorithm will behave in relation to its input size. So with this, it is kind of a simplification. The assumption is that all functions that have the same growth rate will be characterized using the same notation. In practice, we know that even though we have two pieces of code that just have a single for loop, the performance of those two programs could be significantly different. It matters what is happening inside that for loop, but in terms of this algorithmic analysis, in general, we say if it has just a single for loop, we have order big N, or big O of N, the algorithm having that linear runtime, because we simplify all the other so-called constant runtime operations. If I have 47 multiplications and lines of multiplication in my code, and it's not a function of the problem size, that's all going to be considered a constant runtime. Not irrelevant, but doesn't really lead to growth as the problem sizes grow. So these are just some common big O notations you will see in implementation. If you have a single loop, you can think of it typically as order n, big O of n, linear runtime. If instead you have two nested loops, and again, you can do worse than just kind of counting for loops at least to start, you likely have an n squared runtime, because you have the outer loop, which is order n, you have the inner loop, which is potentially also order big O of n, kind of multiplicative property that becomes order n squared. For the binary search, we're kind of cutting the problem in half. That's a log n big O runtime. And there's other examples that we could have as well. It's actually pretty important, because even though at first glance, and we saw this a little bit with the n queens problem last week, at first glance, n squared doesn't seem all that different than 2 to the n, right? They're both kind of exponential in some sense. But if we were just to, and this is just, Excel spreadsheet calculation here, if we had different complexity classes of implementation of algorithms that assume that each operation takes 1 microsecond, that is just an assumption. 1 microsecond is a decent amount of runtime, but it's not an exceptional amount of runtime. This is just showing that if you plug in the big O equations, assuming that for given n values, each operation takes 1 microsecond, here's what the corresponding runtime would be roughly equal to. So if we assume that for order n, we have n operations, each taking 1 microsecond, you'd have a runtime of 10 microseconds. And we can see the linear growth there. If n equals 50, we're at 50 microseconds. When we get to n equals 100,000, we have 100,000 microseconds, or just 0.1 second. That's our linear growth. We plot n versus time for that relationship, we get a straight line with a slope of 10 microseconds. Compared to n log n, you can see there's, actually the one I want to show is just compared to log n, you can see that maybe it's starting at roughly the same place, but the growth is going to be moderated by log n and not by n. So it's going to be better than linear scaling here. Another very common one is n log n, and we'll see quite a few examples of this when we look at sorting, which is there's an initial step that requires kind of partitioning the data in half, like for binary search, but then there's also steps that require kind of combining and looking through that whole subset of data and doing something linear with that data. So you wind up with n log n complexity. In fact, when comparing searches, we're oftentimes comparing order big O n log n versus big O n squared, or order n squared implementations. And you can see the relative growth rates between those two. Doesn't seem like much at first. And again, 1 microsecond is arbitrary. You would get similar growths with 1 nanosecond or 1 picosecond, but still 1 microsecond isn't that much of a time for a single operation here. And it seems okay, it seems okay, it seems okay. All of a sudden, as n grows to 10,000 and 100,000, for our order n squared operation, we get 2.7 hours of runtime associated with that. We didn't see anything running for 2.7 hours, because in Replit it just gives up well before that period of time. But we weren't that far off it. Again, 1 microsecond per operation is quite a bit. It's sometimes hard to think in those terms, but if you have a processor that's running at multiple gigahertz, so it can probably do a lot of stuff in just a few nanoseconds, most likely. But still, it's not that much time. Maybe even divide that value by 1,000 still, and you're still getting maybe a couple minutes of, or many seconds of work required for that order n squared implementation for n equals 100,000. That's for order n squared. We talked about how, for the most part this semester, we're not sweating performance all that much because we really want to get code that's correct and we can understand and we can debug. But going from n squared to n cubed is as simple as adding just one extra for loop, right? Instead of a doubly nested for loop, you have a triply nested for loop because maybe you couldn't quite figure it out with 2 for loops and a third loop was able to get your code to work. But look how the performance kind of changes just by going from quadratic to cubic there. That now for n equals, again, you test it with just a few small values, and maybe it seems a little slow, but it seems okay. As n grows now you're talking days and years for a given implementation, potentially not feasible, right? For those somewhat still modest values of n, now compared to a truly exponential growth rate. And again, 1 microsecond is a lot for an operation. We started to see that for Fibonacci, which the way we implemented it was effectively exponential. Because for Fibonacci of 6, it would have to call Fibonacci of 5, and for Fibonacci of 7, it would call Fibonacci of 6. That becomes exponential. Well, my spreadsheet had a problem with those. It would be a very, very long amount of time to implement anything that is exponential in nature. Sure.
Just out of curiosity, I've seen some places where they talk about maybe like computers trying to like crack passwords.
Sure.
Which big four do you think, or which kind of algorithm do they have projects?
Well, it depends, and there's a whole field of not explicitly trying to guess all possibilities of password, but trying to be a lot more intelligent about it, of doing cryptanalysis and other things. And there's all sorts of really kind of clever approaches that actually, and we won't talk about that at all here, but trade off using a whole ton of memory to make up for otherwise what would take a very long amount of time. So pre-computing a whole bunch of stuff. But if you were, we could do the math, right? If you, let's say you have an 8-digit just alphabetic password with no capitalization in it, that's 26 to the 8 possibilities that we would have to check. If we were to take like a naive approach to password cracking, right? Add in capitals, that's 52 to the 8. Add in numbers, that's 62 to the 8. Now you know what, maybe they want people to add in special characters. There's, I don't know, 1, 2, 3, 4, 5, 6, 7, 8, or 9 special characters. Let's say 70 to the 8th power for just an 8-digit password. If one were to try to just kind of naively check that, well, that would be exponential, right? Not necessarily 2 to the n, but in this case, maybe 78 to the n. And we would see the growth rate would be also completely infeasible to try to just guess every possible password.
So that's why they say a lot of the quantum computers can actually easily like get them.
Well, there's a lot of there's a lot about that. Why people think that certain classes of cryptography would be vulnerable to quantum computing. It tends to be for a very specific reason. So we don't talk about any of this at all either. But a whole bunch of modern cryptography involves what's referred to as public key cryptography, using a set of algorithms that involves having very large composite numbers and factoring them into primes. And when I say very large, I mean thousands of digits worth of very large, relatively prime numbers to each other. And I store one half of that combination, you store the other half, and then we can securely message with each other. That's a gross simplification, but that's roughly what like the RSA algorithm is attempting to do. And the thought and or the fear and or concern is that we have these quantum computers that are being developed both in theory as well as in practice. And one thing they supposedly can do extremely well, because of some hand-wavy reason about quantum superposition of state, is that they can factor integers extremely well, at least in theory. In practice, I don't believe someone's built a quantum computer that can factor more than 15 yet. So like 3 times 5 equals 15 is like the limit of what they can do. But in theory, that would be a concern, that if we had real-world practical quantum computers, the type of cryptography that relies on calculating and storing very large prime numbers would be somewhat vulnerable and somewhat instantaneously so. think we're okay for a little while. Determining big O. Let's look at our old friend. I think we can call him our old friend at this point, the bubble sort. Um, Others will call the selection sort. The only difference is which order your I and J loops are. So I'm okay calling it bubble sort all semester, even though you may see the same exact code being referred to as selection sort. We know this code. We have our value of n or num values. We have our outer loop that we're going to do this operation n times. We have our inner loop, and in fact, we introduced this as a slight optimization because each time through that inner loop or through that outer loop, we have one value fully sorted. So we're putting things in the right location. We check to see if our neighbor is actually greater than the one next to it, and if so, we swap those two values. And in doing so enough times, we wind up with a sorted array. We can do a lot worse than just counting the size of our for loops in terms of determining the big O complexity. Again, you take a class like ComSci 311, you're going to do a much more formal job of understanding that. But in this case, we know we have an outer loop and we have an inner loop. So we're going to have n inner loops, or num values inner loops here. First time through that inner loop, our value of j is equal to 0. So we have n minus 1 things getting done in that inner loop. Next time through, we have n minus 2. Next time through, we have n minus 3, all the way down to a value where we get just 1 back out. Well, you add that together, you get n minus 1 times n over 2, or equal to n squared. And again, technically it's n squared over 2, but in terms of our analysis, we treat anything that grows at that quadratic level as being exactly the same. So our big O is still n squared for that case. If we were to plot the runtime of our old friend the bubble sort as with n as our x-axis, we should see a quadratic curve where it's pretty fast early on, but over time it's going to look close to that fourth row in this particular table here. The only difference is that assumption of 1 microsecond. It shouldn't take nearly 1 microsecond to do the inside of this for loop. It's got an if, a couple memory lookups, a little swapping operation. It should take on the order of nanoseconds to do that for loop. But that's the only difference. It's still going to be that quadratic growth that we have here. Sorting is a very fun thing to learn, but it does generally require an entire course to learn properly. It's just a really good way to demonstrate the difference between fundamental approaches to algorithms. There are many, many different algorithms for sorting that have different algorithmic complexity and different corresponding runtimes. Some of these are more kind of funny proof of concepts than actual things that are used. But BOGO sort is just shuffle and pray. Pray in quotes meaning randomize the values, and if it happens to be sorted, you're done. So that is technically one way to sort an array, and we can actually calculate the complexity of it. We have three very similar sorts of selection sort, insertion sort, and our bubble sort. Find and sort one element at a time is basically what all three of those are doing. And we're going to look at a couple of the more logarithmic sorts. Specifically, we're going to look at merge sort and our quick sort, which is by dividing the array in halves, can we get that half sorted and then just combine the values back out? Dividing in half is going to be log n, like we saw with the binary search. Combining back is going to be order n. We're going to wind up with performance of these of all order n log n. And then depending about what features or facts you can assume about the data, there's all sorts of other sorts that are possible. And it's still kind of an active area. I mean, it's a very textbook kind of topic to study, but people who are kind of in the field and trying to sort things as quickly as possible are still exploring new approaches. I like radix sort. We won't implement one this semester, but the idea is if I know my data is integers of a particular range, I can sort everything by first digit, then by next digit, then by the next digit. And then our runtime is actually a function of how many digits I need versus the actual size of the particular data. And then there's an XKCD of ineffective sorts, including panic sort, which I like. I don't know how well you can read that. You can look at it later. But by the end of panic sort, the person gives up and just removes all the files on their home system, and then just gives up at that point. Shuts down the computer and returns 1, 2, 3, 4, 5. At the end. The joke is also this is a common job interview question. I don't think it's that common of an interview question any longer. When you get, and you will have this opportunity when you get your first real technical internship or full-time interview, they will try to test your coding background, and so they'll try to ask you things about linked lists and the like. My advice is always just to be honest. They want to see your thought process more so and how you handle kind of a pressure situation of being asked to do something versus does this applicant know exactly how to do the perfect sort given this particular scenario? So keep that in mind. You can study, you can prepare, you can kind of cram for everything in the book of algorithms before a given interview. And then your interviewer, if they're sufficiently clever, could still come up with something that you wouldn't have seen before. So being able to think on your feet, being able to kind of have a conversation is way more important than making sure you get the exact right algorithm when it comes time to answer a technical interview question. So the big picture, how these algorithms tend to look like in practice, you have your so-called bucket of so-called simple algorithms. I like this visualization. We did not implement insertion sort, but it's going to have that same kind of runtime as our friend the bubble sort here. You can restart that simulation here. The idea being an insertion sort, and we'll walk through the algorithmic notation for it. We're inserting each value at a time where it needs to go. It's color-coded, but this purple one's going to come, we determine that it has to go here, we shift everything correspondingly. We'll have a subarray that is sorted and a subarray that is unsorted. That's an iteration of size n we have to do each time, and we have to do that n times to sort every value. We wind up with that whole class of order n squared types of algorithms, which again, going back to that table or even just our own experiences with bubble sort, can be fine. It's not inherently wrong. It's easy to understand and explain and easy to code, but as n grows, that may in fact be a very slow and tedious process. There's also the class of quote unquote fancier algorithms, the n log n class of algorithms. And with these algorithms, there is some way, shape, or form in which there's this binary division happening. That's where we get the log n side of things. It's not my visualization, but a visualization of merge sort. And what we do with our merge sort, and we'll get to that at least, if not today, on Wednesday, what we do with our merge sort is we just subdivide. And then we subdivide, then we merge things together. Subdivision is log n. Merging things back together is linear. And you can see as we do it, you can do it recursively. We wind up with those whole swaths of that array being sorted. Then there's the really kind of specialized algorithms that you would look at and say, well, why don't we always just use radix sort? Well, radix sort and some of these other kind of specialized algorithms make certain assumptions about the data that is our input that aren't always going to be the case. With radix sort, we're basically taking multiple passes over the data and determining what are all the values. I'll show that again pretty quickly here. What are all the values that start with 1, put them in one bucket? What are all the values that start with 2, put them in one bucket? And that can be done with just really a single pass. Grab the digit, put it in a corresponding bucket. Then for each bucket, grab the next digit and put it in a corresponding bucket. So you have your 1 bucket, then you have your 1, 2 bucket, or then you have your 1, 1 bucket, then you have your 1, 1, 1 bucket, and ultimately you have your values that are going to be sorted at the end of the day. That can be quite a bit faster than even your merge sort, but if your data doesn't fall into that nice pattern of being just integer values for which there's a known width of the data that you're going to be limited to, you really can't use it. And then in reality, what tends to be the case when we look at algorithms is that really depends on the size of your data. Once your data becomes something that doesn't really necessarily fit nicely into the memory that's going to be operating on the machine you're running your code on, you have to think about completely different approaches, which is partitioning, parallelizing, doing in part, and then some separate merger. And that's roughly external sorting. When you start to take potentially classes in things like high performance or parallel computing, you start to realize that these algorithms are all very well and good, but then once implemented in practice with real machines, with real limitations, you have to really think about external issues as well. Let's leave things here for today. I know cutting short a little bit early. I want to cover a couple of these sorts. We'll implement a couple of these sorts on Wednesday. And I want you to be able to see the performance of it, but I want us to take our time and do it properly. So let's leave things here for today. We'll cover insertion sort, sort, merge sort, and quick sort. And we'll see the relevant performances of all three of them on Wednesday. And that'll pretty much be it for the semester, notwithstanding your final projects, which I can't wait to see. Okay, thank you.